Imagine this. You walk into a dark room, you flip a switch, and instantly the light turns on. It feels obvious, normal, almost boring. But pause for a second. Let's really think about what just happened. That switch in your house is connected to wires that stretch kilometers away, all the way to a power station. So here's a strange question we almost never ask. When the light turned on, what actually moved? Did tiny electrons race from the power plant to your bulb at near light speed? Did energy travel through the wire like water through a pipe? Or did something else happen? Something invisible, something we never notice. Because if electrons really had to travel all that distance, your room shouldn't light up instantly. It should take time, maybe seconds, maybe minutes. Yet it doesn't. The light responds immediately, as if the wire already knew what you were about to do. So ask yourself this slowly. When you flip a switch, did something really travel all this way instantly? Or have we been misunderstanding electricity all along? Let's start unraveling that illusion. The moment you flip a switch, it feels like something just rushed through the wire and reached the bulb. Most of us imagine the same picture without even realizing it. Tiny electrons sitting near the switch suddenly wake up and sprint through the wire all the way to the bulb, lighting it up as they arrive. It sounds reasonable. It feels intuitive. But this picture is completely wrong. Let's slow the moment down. That wire in your wall is already full of electrons. It's packed like a crowded train at rush hour. When you flip the switch, you're not releasing fresh electrons from the power station and sending them on a long journey to your room. Instead, something much subtler happens. Imagine holding a very long wooden stick. You push one end gently. Instantly, the other end moves. Now ask yourself, did the wood from your hand travel all the way to the far end? Of course not. The stick barely shifted. What moved was the push, the disturbance, the signal traveling through the stick. Electricity works in a very similar way. When you flip the switch, electrons near the switch barely move at all. They just nudge their neighbors. Those neighbors nudge the next ones, and so on. No electron makes a heroic journey across the city. Each one just jiggles in place, passing along the effect. This is the switch illusion. We confuse movement of particles with movement of influence. The light doesn't turn on because electrons are racing fast. It turns on because the electrical influence spreads through the system almost immediately. Once you see this, the whole idea of electricity starts to feel less like flowing water and more like a coordinated response. And this raises a new, unsettling question. If electrons themselves are barely moving, then what exactly is spreading so fast through the wire? That's where things get really interesting. Because next, we'll discover just how shockingly slow electrons actually are, and why that fact changes everything. Now here's the part that almost nobody believes the first time they hear it. Those electrons we imagine rushing through the wire, they are actually moving painfully slow. Not slow like a bicycle, not even slow like a walking human. In many household wires, an electron drifts only a few millimeters per second, sometimes even less. That's slower than a crawling ant. So let that sink in. If you turned on a light and waited for the same electron to travel from the switch to the bulb, you might still be waiting tomorrow. And yet the bulb lights up instantly. So what's going on? Picture a long, crowded hallway filled wall to wall with people. Everyone is standing shoulder to shoulder. No space to run, no space to sprint. Now the person at one end gently leans forward. They don't move much, but the pressure passes to the next person. And the next. And the next. Within moments, the person at the far end feels the push, even though no one actually ran down the hallway. That's exactly what electrons are doing. Each electron barely shifts from its position. But because the wire is already full, that tiny movement forces the next electron to respond. The effect travels quickly, even though the particles do not. This is the key truth most explanations skip. Speed in electricity is not about how fast electrons move. It's about how fast their influence is passed along. The current responds almost instantly, even though the electrons themselves are taking their sweet time. Once you understand this, something clicks. Electricity isn't a race. It's a conversation. And now comes the most important question of all. If electrons are just slowly shuffling, what is it that's actually doing the talking? To answer that, we need to meet the invisible messenger that makes electricity possible. Up to now, electrons have been getting all the attention. But here's the quiet truth Richard Feynman loved pointing out. Electrons are not the main characters in this story. The real hero is something we can't see, can't touch, and almost never imagine. It's called the electric field. When you flip a switch, the electric field inside and around the wire rearranges itself almost immediately. That rearrangement is what carries the energy. not the slow drift of electrons. To feel this, imagine a long rope stretched tight between two people. The rope is already there, already connected. You give one end a sharp tug. The other end responds instantly. Not because rope material traveled from your hand to the other person, but because tension changed along the entire rope. Electric fields work the same way. The moment the switch closes, the electric field adjusts throughout the circuit. Electrons feel this field and respond locally. Just tiny nudges, nothing dramatic. But the energy rides on the field itself.
Here's the strange part.
The energy that lights the bulb doesn't crawl inside the wire like something in a pipe. It moves through the space around the wire, guided by the wire. The wire doesn't deliver energy. It tells the field where to go. This is why electricity feels instant. Fields respond far faster than matter can move. Once you see this, a deep realization sets in. Electricity isn't about things traveling. It's about conditions changing. And suddenly, the wire starts to feel less like a container and more like a signpost, which leads to an even more unsettling idea. If energy is flowing through the space around the wire, then what exactly is the wire doing at all? That question takes us to one of the most counterintuitive discoveries in physics. By now, the wire itself is starting to look suspicious. We've been treating it like a tunnel, as if electricity lives inside it, trapped, rushing forward. But physics tells a very different story. The wire is not where the energy mainly travels. The energy flows in the space around the wire. This sounds impossible at first, so let's slow it down. Think of a water pipe. We say water flows in the pipe, but what really makes water move is pressure. Change the pressure at one end, and the effect spreads throughout the system almost instantly. The pipe doesn't create the pressure. It only shapes where the pressure goes. A wire works the same way. When the electric field forms, it spreads through the space surrounding the wire. The energy moves along that field, hugging the wire, guided by its shape but not confined inside the metal. The electrons inside the wire are like signposts. They respond to the field and help maintain it, but they are not carrying the energy on their backs. This isn't just a clever idea. Engineers can actually calculate how much energy flows through the empty space around a wire, and the numbers work. Remove the space, disturb the field, and the circuit fails, even if the metal is still there. That's a strange feeling. It means electricity is partly happening in empty space, in something that looks like nothing at all. Once you realize this, the everyday picture of electricity collapses. The wire is no longer the hero. It's the guide. And this is exactly why Richard Feynman warned us about explanations that feel too comfortable. Because when an explanation feels too simple, it often hides the most important truth. And that takes us to why Feynman himself hated the usual way electricity is explained. Richard Feynman had a strange habit. Whenever someone gave a very neat, very simple explanation, he became suspicious, especially with electricity. You've heard the line, "Electricity flows like water through a pipe." It sounds friendly. It sounds helpful. And that's exactly why Feynman disliked it. Because once your brain accepts that picture, it stops asking questions. Calling electricity flowing water is like standing at the beach looking at the ocean and saying, "It's just water." Yes, but also no. That one sentence quietly erases waves, tides, currents, storms, and deep invisible motion beneath the surface. In the same way, the water analogy hides the electric field, hides energy flow in space, and hides what actually makes electricity work. Feynman didn't hate simplicity. He hated fake simplicity, the kind that feels satisfying but prevents real understanding. He believed that if you can't explain something without lying to yourself, then you don't understand it yet. Electricity doesn't behave like water. It doesn't pile up, slosh around, or leak the same way. What matters is not stuff moving, but relationships changing, fields adjusting, influences spreading, systems responding together. This idea forces a kind of humility. It reminds us that nature doesn't owe us easy metaphors. Sometimes reality is subtle, and we have to be patient enough to meet it there. Once you accept this, a powerful shift happens. You stop asking, "What's flowing?" and start asking, "What's interacting?" And that change in thinking doesn't just improve understanding. It's the reason modern technology works at all. Because the moment engineers stopped thinking in water analogies, they unlocked radio, antennas, power grids, and satellites. And that brings us to the real-world proof, where these invisible fields quietly run the modern world. At this point, everything we've talked about might still feel a little abstract. Electric fields, energy in space, invisible influences. So here's the real test. If this picture is true, does it actually matter outside a physics classroom? The answer is your entire modern life depends on it. Look at a power grid. Electricity isn't pushed from a power plant and slowly delivered house by house like parcels. The grid works because electric fields establish themselves across vast networks almost instantly, guiding energy where it's needed. This is why engineers obsess over spacing, geometry, and surroundings of wires, not just the metal itself. Change the environment around a cable, and you change how energy flows. Now think about radio and antennas. When a radio station broadcasts music, electrons in the antenna barely move. What they create is a rapidly changing electric field that ripples outward through space. Those ripples travel across cities, mountains, even oceans. Your phone doesn't catch electrons. It responds to a field that was shaped far away. GPS makes this even clearer. Satellites orbiting Earth send signals that rely on precisely timed electromagnetic fields. Your phone calculates position by reading how those fields arrive, not by tracking particles flying through space. If engineers believed electricity was just electrons flowing like water, radio would be unreliable, GPS would drift, and power systems would behave unpredictably. But they don't. They design with fields in mind. This is the quiet proof. Every call you make, every navigation app you trust, every light that turns on without delay, all of it works because we learned to think beyond visible motion and focus on invisible structure. And once you see that, a deeper question starts to form. If electricity, something so physical and everyday, is really about invisible fields and relationships, then how much of reality itself works the same way? That question takes us to the final realization, one that changes how we look at the world altogether. By the time we reach this point, electricity no longer feels like a simple household utility. It starts to feel like a lesson. Because electricity quietly reveals something unsettling about reality itself. We like to think the world works because things move. Cars move, balls roll, particles travel from here to there, but electricity shows us a deeper pattern. Often nothing important is traveling at all. What's changing is the relationship between things. When you flip a switch, electrons barely drift, yet the entire system responds. Not step by step, but together. It's as if the universe is woven from an invisible web. Touch one part and the whole pattern adjusts. This idea appears again and again in physics. Gravity isn't a rope pulling planets. It's a relationship shaped by space itself. Light doesn't need a road. It's a ripple in fields that already exist. Electricity trains us to stop asking, what object moved? And start asking, what interaction changed? That shift is quiet but profound. It means reality isn't just a collection of solid things bumping into each other. It's a network of influences constantly responding, even when nothing seems to move. Once you see this, the everyday world feels different. Wires feel less like pipes, space feels less empty, and nothing happening starts to look like an illusion. Because beneath the surface, relationships are always adjusting. Electricity doesn't just power our homes. It rewires how we understand the universe. And maybe that's the most surprising part of all. The world doesn't run on motion alone. It runs on connection. So the next time you flip a switch and the light turns on instantly, you're not just using electricity. You're watching reality respond. So let's step back and look at the whole picture. We began with something ordinary, a light switch. A moment so familiar that we never question it. But as we followed it deeper, the story changed. We learned that electricity isn't electrons racing through wires. That electrons themselves move slowly, almost lazily. That the real action happens through invisible electric fields. That energy doesn't live inside the wire, but flows through the space around it. That simple explanations can quietly block real understanding. And that the technologies running our world, power grids, radio, GPS, work only because we learn to think in terms of fields and relationships. All of it points to one quiet realization. Reality is not just made of things. It's made of connections. Much of what matters most happens invisibly. Before motion, before contact, before anything we can easily point to. Electricity didn't just teach us how to light our homes. It taught us how the universe prefers to work. Not by rushing objects from place to place, but by letting relationships adjust across space. So here's a thought to leave you with. If something as everyday as electricity is really about invisible interactions, how much of reality around us is shaped by things we don't see, but feel the effects of every single day? I'd love to hear what you think.